Welcome back to ECE 320A. Homework number 3 is due Tuesday of next week, and that's dealing with Laplace transforms. Your second exam will occur after spring break, maybe a couple of weeks after spring break, but it will be upon us before we know it, and I want to make sure that that's in or on your radar screen or in your calendar. And we will have homework assignments 4 and 5 prior to exam number 2. And you can look at those already. Those are already available in mastering for you to examine or see what's been assigned and what you're responsible for on the exam and for the homework. What we want to do today is continue with Laplace transforms, and I want to simply remind us of where we left off last time was a table of Laplace transforms, and they all arise from just from Laplace transforming an exponential. And then we let that exponential constant be real, positive, real negative, imaginary positive, imaginary negative, and then we can combine those however we want to create Laplace transforms of useful waveforms that we might want to have available to us. I'll then try to give you a big picture overview of Laplace transforms. Where does it, or what does it position us to do in terms of analysis or understanding or use? And that's the marketing, the advertisement, the commercial. That will happen shortly after looking at the table of transforms. Then I have to wake you back up after the commercial with a quiz, and that quiz is going to see, do you now have in your mind these transform pair relationships? And if not, you better before exam number 2. Okay? But you will, I think, be provided a table to help you with that transform pair relationship, either doing Laplace transforms or inverse Laplace transforms on exam number 2. If the transform pairs are not exactly as you want them in the table, you may have to do some transforming to make them appear like what you're given as a problem. And that's what these operational transforms are for. How do we manipulate these either transform expressions or the time domain expressions to make them look like something that we can see in rows of the table and make that connection? Then we'll get on a ladder. Actually, how many have done ladder analysis with circuits? That's kind of what I expected. No hands were raised, or, well, I should put my, have you heard of it?
No, I never raised. I did the same.
Oh, you raised your hand?
No, I did. I have a good one.
You do have your shin guards?
Yeah.
Yeah. So we'll talk about using ladder analysis to perform some circuit analysis. And that's how do we really work from an output variable back towards the source. And that working back is working our way across a ladder that's now lying horizontally. We're not going to go vertical with the ladder. We're going to do it horizontally. But we'll step through the rungs of a ladder to get from the output side to the input side. We'll then start looking at how do we go back and forth, or how do we now find time domain waveforms associated with particular transform expressions. That's the inverse. How do we go from the living room back into the kitchen? If we were in the frequency domain, how do we get back into the time domain? That's inverse Laplace transforms. Here was one of the key results that we derived last time from the definition of the Laplace transform. What's the Laplace transform of e to the gamma t? It's 1 over s minus gamma. Let's now examine that in a little bit more detail relative to the time domain waveform. And I believe last time I kept trying to give you this, what do I want to say, animated way of thinking of an exponential. Weren't we doing something like that the last time? Here is the exponential, e to the minus sigma t, and how quickly it decays exponentially is influenced by how big sigma is. E to the minus 2t does not decay as fast as e to the minus 10t, for example. But you might also see this written, this decaying exponential, in what's called time constant form, e to the minus t over tau, where tau is the time constant. If you compare the right two pieces in that expression for x of t, hopefully you see the algebraic relationship between what I might call the damping, sigma, and the time constant tau. They're inversely related. One is the inverse of the other. If you know sigma, if sigma is 2, then you know the time constant is 1/2. And that time constant has units of time. It's in seconds typically. We want the exponent to be dimensionless. T is upstairs divided by something. The units of that something downstairs needs to be consistent with the time in the numerator of that exponent. So that now if we had a time constant of 1/2, if little t, if we've now progressed one time constant in to that exponential waveform, we now have e to the minus 1/2 over 1/2, or e to the minus 1. Do you remember what e to the minus 1 equals? 1 over e. Correct. Yes, it is 1 over e, but e is about 2.7, so it's 0.367, something in there. So it's a little bit more than a third, e to the minus 1. Let's now use that thinking to better understand this example. Here's an example of a decaying exponential, e to the minus 2t, that starts at time 0. Sigma is 2. The time constant, tau, which is 1 over sigma, is 1/2. Or if somebody says, what's the time constant? If you now have e to the minus something, you set that something, that exponent, equal to 1, and you solve for the time that causes that quantity times t, which now I've replaced t with tau, to equal 1, or tau now is 1/2. That's another way of thinking about how do I find the time constant. The time constant is the value of time t that allows that exponential piece, the 2t, to equal 1. That would be one time constant. In this case, for e to the minus 2t, we have a time constant of 1/2, 1/2 of a second. You might hear us, and we'll be doing this probably before exam number 2, so I want to try to get us thinking that way. The 1% settling time, or if you initialized a capacitor, let's say, and you said, when is it going to be 1% of its starting value? Well, that will occur after 5 time constants in, let's say, an RC circuit. Where does that come from? Well, if we take e to the minus t over tau, and we let t be 1% settling time, which we're defining to be 5 tau. This is an approximation. It's not exact. Then we end up with e to the minus 5 tau over tau. The tau's cancel, and we have e to the minus 5. And I'm sure you now know what e to the minus 5 is. It's 1 over e to the 5th. Yeah. But numerically, that's now 0.006738, and that's the approximation that we're making. We're saying that 0.007, we're just going to say that's roughly 1%. That's roughly 0.01. That's where the 1% settling time comes in from 5 time constants. You might have somebody say, oh, it's 2% settling time. Well, that's 4 time constants. But let's just stick with our settling time being 5 time constants. In this case, if our circuit actually had a time constant of 1/2, we would say, well, essentially, the waveform is gone when we have crossed 5 time constants, or how much time? 5 times 1/2, 5/2, or 2.5. So in 2.5 seconds, we essentially have all of our transients gone from our circuit. And 1/2 being a time constant is very, 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 very big in electrical terms. It's usually a time constant is much smaller than that. And so when you excite a circuit or initialize a circuit, it doesn't take long for those voltages and currents to die away, to become gone. Or what do we consider to be gone? When they're 1% of where we started after 5 time constants. And I sort of joke, I never joke around, but if I say when is infinity small, well, in electrical engineering, infinity is actually 5 time constants, and if your time constant is 1 millisecond, in 5 milliseconds, you've now reached an infinite length of time, effectively, because you've now decayed away. So infinity, well, it's not very big. It's 5, whatever I just said, milliseconds. Yeah. So is that clear? If I say a 5% settling time, you know that it's 5 time constants, and you now know how to find the time constant if you're given a decaying exponential. That's what I want you to, one of the things I want you to take away from today's class. How do you find the time constant, and what good is it? How can you use it? So here is what I was just saying. And I spent 30 minutes trying to draw this exponential. Should have just put it in MATLAB and done it, but I was trying to do it by hand, and that's tedious. Pardon? No, I spent more than 5 tau. I spent more than 2.5 seconds drawing that exponential. So it took longer to draw than it actually lasts. But this is now e to the minus 2t. After 1 time constant, which is 1/2, we're at basically 37% of where we started. And then we just keep knocking that 37% down by 37% at each time constant. And after 5 of those, 1, 2, 3, 4, 5, we're at 2.5 seconds, which this is probably bigger than it really needs to be. That's now 1% of where we started up here in our trajectory or in our waveform. And that's what we calculated. If our time constant is 1/2, our settling time is 2.5, and that's essentially after all the transients have disappeared, is after 5 time constants. So in 2.5 seconds, we can say we've decayed. Everything is gone. Yes?
So are we always going to set the exponential to 1 when solving for tau?
Yes, the question was, are we always setting the exponential? So if you had to 1 when we're solving for tau, if we did, I don't know what color I'm using, suppose that we had e to the minus 6t. What's the time constant? You could do it many different ways, but the one that was just asked is, can we do that? So when t is equal to tau, that's how we'll find our time constant tau. We just replace t with tau and set that 6t, that exponent, equal to 1. And now tau is equal to 1/6. And 5 time constants is less than a second now, if we had a decay that was corresponding to e to the minus 6t. We would now be 5/6 of a second for our settling time, our 1% settling time. Other questions? Actually, I'm going to erase that because somebody will go, where did that come from? If they're looking at the notes, since I can see not everyone is in attendance today. I guess it's too cold for them to come to class. Any questions on settling time and time constant? Those ideas, those concepts, that picture, you need to be comfortable with. Here's the table of transforms that we played with last time. We have a exponential decay, e to the minus sigma t. It gives us a frequency domain transform of 1 over s plus sigma. If sigma was 2, we would have 1 over s plus 2, and this pole would be at minus 2 in the complex s-plane. If we had a exponentially growing waveform, e to the 5t, that's going to go unbounded rather quickly. It corresponds to 1 over s minus 5, and the pole is where the denominator, or when the denominator, the value of s when the denominator is equal to 0. And in this case, it would be when s is equal to 5. Then we become a little bit more creative, and we say, what if this gamma in e to the gamma t is actually imaginary? What if it's j omega? Omega now is our oscillating frequency. We Laplace transform e to the j omega t, and we actually obtain a 1 over s minus j omega for its Laplace transform expression. We set the denominator equal to 0 and solve for s to find the poles. And this now says, oh, s is equal to j omega. This now corresponds to a j omega above the horizontal real line. Corresponding to that, or its twin, is if we looked at e to the minus j omega t. Then we have 1 over s plus j omega. We set that denominator equal to 0, and the s is now minus j omega, so now we have the twin, or its conjugate, location down below the real line. And I think last time I mentioned, when you have polynomials that have real coefficients, the roots of those polynomials are always going to appear in conjugate pairs. If you have a minus 3 plus j7, you'll have a minus 3 minus j7 as your two pole pairs that are complex. That's the table. And from that, the bottom two lines of that table allow us to actually use those complex exponentials. And who are we crediting with giving us that useful formula? Euler, our friend. So cosine omega t we can write as a linear combination of two complex exponentials, the plus and the minus. Doing that, we end up with the Laplace transform being s over s squared plus omega squared. In the time domain, I'm now trying to sketch what that cosine looks like. And here, this t is the period of that cosine waveform. That's not the settling time. Does this ever settle, cosine omega t? This is chapter 9, isn't it? This is sinusoidal steady state. So you've reached now a steady state. It's not decaying. You're now hitting a system with something that's at this particular frequency, omega, for all time. And now it's caused every element in your circuit to be oscillating at that omega. They may be shifted in time relative to the input, but everything in that circuit, since it's a linear circuit, is oscillating at that frequency omega. So we know the relationship between the period of that waveform, which we said is t, and what omega is. Meaning if I now drew a cosine waveform on an exam and said, oh, find the Laplace transform, you could now figure out what omega is based on measuring the period of that waveform. Omega is now 2 pi over cap t, and once you know omega, you have the Laplace transform. S over s squared plus omega squared. Which, that transform wave, well, let me just say function, s over s squared plus omega squared gives rise to a 0 at the origin. That's the value of s that causes the numerator to vanish. And it gives rise to 2 complex conjugate poles right on the imaginary axis at plus and minus j omega. As the frequency omega gets bigger, as that sinusoid gets faster, where do those poles transition to? Closer to the origin or further away? It's not a difficult question. They get further away, don't they? They go closer to infinity. As the frequency gets higher, those poles now move further away from the horizontal real line. I think every one of you went home Tuesday and derived this. Don't admit if you did not, because I think everyone from your facial expression last time, you just couldn't wait to get home and derive the sine of omega t. I saw it in your eyes. So sine of omega t is similarly derived, but now what happens to its transform? What's consistent with the sine and the cosine? Their poles are exactly at the same location, aren't they? If it's at the same frequency. The denominator is s squared plus omega squared. Here's our time domain waveform. There's our frequency domain plot. And what's different in this frequency domain plot versus the cosine? Do I see any answers here anywhere? There's no 0, is there? There's no finite 0 on that complex S-plane. There's no finite value of S that causes that sine's Laplace transform to vanish. You just have the 2 poles. And again, you could physically measure in the time domain this period of oscillation and use that period to figure out what the frequency of that sinusoid is equal to. I want you to start getting comfortable with time domain waveforms. Oh, a sinusoid. You can visualize that in your head, and then you can see where its poles are in the complex plane. Let's step it up a notch. We've talked about exponentials. We've talked about sine and cosine. Let's put them together. An exponentially damped cosine. And these you see all the time in electrical and computer engineering. And we'll play with exponentially damped sines and cosines. And I may just say an exponentially damped sinusoid. That incorporates a sine and a cosine that's exponentially damped. It now is exponentially damped by this envelope. The envelope of damping is what I'm trying to indicate with the green dashed lines. That envelope is determined by the e to the minus sigma t. And now you could tell me what's the settling time of this waveform based on whatever sigma is, right? Sigma is inversely related to the time constant tau. And if now you know e to the minus sigma t cosine omega t, you know after how many seconds this waveform will basically be gone. After 5 tau, and you can figure out tau from sigma. Tau is 1 over sigma. Likewise, you could measure how fast this is bouncing back and forth. It's bouncing back and forth, but it's also decaying. But the bounce, so the distance between peaks or the distance between valleys, the distance between two similar points on that sinusoid tells us our period of that sinusoid. That now allows us to find omega. When you see this exponentially decaying or damped sine or cosine, I want you to be able to visually think about what that looks like. And that's the picture. What does its Laplace transform look like? And we'll look at how we can obtain this by using operational transforms later. But for now, let me just say that instead of putting S, we replace S with S plus sigma, the amount of decay, in our cosine. Our cosine without an exponential decay was S over S squared plus omega squared. Now with this exponential damping, we in fact just replace the S's everywhere with S plus sigma. And what does our pole pattern look like? Pole zero pattern look like? In the S plane, now everything is shifted into the left half plane by the amount of damping sigma. The more damping we have, the farther those poles are into the left half plane. The further those poles are into the left half plane, the faster or slower your response is. Is that question clear? Here's the S plane. And I'm really asking the following. If I had poles here, and then I had another set of poles here, which set of poles, yellow or blue, are faster? By that I mean, which decay quicker? So we're getting a couple of, and this just is 50-50, right? You could pull a coin out and flip. One side of that coin is yellow, the other side is blue. So it's not too... All right, so here, let me see if I can get an answer without everybody blurting out just yet. I'm going to have you class participation. We'll do it with thumbs. Okay? Yellow is up, blue is down. And I want that thumb to be held close to your body so that everybody doesn't see, oh yeah, that's my answer after I see everyone else's answer. Or is it, so I'll count to 3, and at the count of 3, I want you to show me your thumb either up or down. Is that clear? What are the choices? So what I'm asking is, which of these poles pairs are faster? Which decay more quickly? That's what I'm meaning by faster. Is it the yellow pair? That would be a thumbs up. Is it the blue pair? That would be a thumbs down. So which of these pole pairs, yellow or blue, are faster? Is the question clear? All right. Get ready. Are we ready to answer? 1, 2, 3. Show me your thumb. Thumb. Now I forgot what I said was which. Yellow was thumbs up. So boy, the coin was pretty fair. I see about 50% of you with thumbs up and 50% of you with thumbs down. You think you're not thinking, huh?
I think they did the same.
One of these days I may keep going, huh? And that shin guard. You wear Kevlar? Yeah, that's good. The blue is actually faster. Why is that? And if you don't quite get it, I would say, oh, let's make this e to the minus 10t, and let's make this e to the minus 5t. Which one becomes smaller quicker? This is now out at minus 10, the blue. This one's at minus 5 for the yellow. And e to the if you plug in the same t value, you now have, let's say we plug in t equal to 1. We're now looking at e to the minus 5, which isn't very big, but e to the minus 10 is even smaller. And so after 1 second, the blue has decayed more quickly, or it's faster than the poles in the yellow. Isn't the blue on what? Oh, I was talking about the blue highlight. I'm sorry. You were thinking of the blue poles. I'll put that on the next exam. I'll have all different colors and ask you. So here I was meaning the blue highlight. So I had the red X's is what I was hoping we were comparing. Apparently that wasn't clear, so I apologize. But this set of red X's, I wasn't even seeing the blue. I had put on my filters, and I wasn't seeing the blue. So maybe that's why it was half and half. Yeah, just argue that. Okay. But now is it clear if we're just comparing the red ones, forget the blue ones, I've erased those virtually. Put on your augmented reality headset, and those aren't here anymore. Those blue X's. We just have the reds, and the blue shaded or the blue highlighted red poles are faster. We're not even, and I could cover up those blue ones. See, you can't even see them, can you? Now I have them covered up. Doesn't work to cover up on the tablet, does it? All right. Well, I'm going to get rid of those because somebody's going to go, what's he talking about faster? And now we do have blue poles. Where are we? Okay. So now we're ready for a discussion, a commercial on the Laplace transform. And we're in the kitchen and the living room. And I don't remember which is which, but one is the time domain, one's the frequency domain, and they are connected by this Laplace transform operation. If you now want the frequency domain information about a signal or a waveform, little f of t, you plug it into this integral. You scale f of t by this complex exponential e to the minus st, or you weight it for all time and all frequency and integrate time out. You integrate over all time from 0 to infinity. Time has now been, you look at this waveform over all time history and you say, what kind of frequency content are you going to give me? Well, it gives it to you in this expression, capital F of s. So we'll have a time domain waveform, and we'll have its pair in the frequency domain, capital F of s. And we need to get comfortable thinking back and forth between time domain and frequency domain. We will initially concentrate on using this Laplace transform to help us with circuit analysis. Instead of solving differential equations, we'll be able to do algebra with this complex frequency variable s. And once we get an answer that may be a ratio of polynomials in s, we want to then take that back into the time domain by inverse Laplace transforming. But we didn't have to solve explicitly differential equations to get that. We also will use the Laplace transform throughout this course, so you can't just learn it and forget it. You have to learn it and remember it and be able to use it for the duration of the class. So, transfer functions. Have you seen transfer functions? If you have not, we will get to those in Chapter 13. Here is a low-pass filter, 10 over s plus 10. That's a low-pass filter. We'll deal with filters in a later chapter, but that's one transfer function, h of s. We will immediately, and we've already talked about poles and zeros in chapter 12. That's what Laplace transforms allows us to do. For this h of s, we don't have any finite zeros. There's no finite value of s that causes h of s to vanish or causes the numerator to disappear. There is a value of s1 that causes the denominator to vanish. If the denominator was a power of 6, it had s to the 6th, then you would have 6 poles to worry about, 6 poles to deal with. Some of those could be complex conjugate pairs of poles. Or you might have a 4th order denominator, then you have 4 poles. This is now a 1st order low pass filter, because the s is just raised to the 1st power. We will also learn about Bode plots, and this is back in an appendix of your textbook. Here in the black line is 1/2 of a Bode plot. Bode plots will consist of a magnitude plot with respect to frequency, and typically it's log omega, log frequency. That allows us to look at many, many more frequencies over a shorter horizontal distance when we take the log of omega, and it also allows us to draw straight lines. Meaning, this particular Bode plot is of the h that we had before, but now do you see what we've done with s? We've replaced s with, where are we on the imaginary axis? We're forcing s to be equal to j omega. This h is now really, we're evaluating h of s at every point along the imaginary axis, and we can do that very quickly with a Bode plot, knowing how to sketch Bode plots. Here it will be flat at 0 dB until we reach the cutoff frequency, or the bandwidth of our low pass filter, which was 10. That's where the pole was located. And then we start rolling off. And we roll off if we simply have one 1st order factor. We're rolling off at 20 dB per decade. A decade is a multiple of 10. Meaning, if we start rolling off at 10 radians per second, then if somebody said, oh, what's the magnitude at 100? Then we would say, oh, we just transitioned down 20 dB in 1 decade. At 100, we would be down at minus 20 dB in magnitude. If I said, what's the magnitude at 1,000 radians per second? That's now 2 times this, because now we're 2 decades beyond where we started. Yes? So what does this symbol mean, I think, is the question. This, and if you're listening to this, you have no idea what symbol I just pointed to. It's the little stair-step blue symbol on the slope. That's just a way of indicating this is telling you what the slope change is. What's the rise over run, or in this particular example, it's how fast are we going down as we go across horizontally. We're going across a decade, and if we do, we go down 6 dB. I'm minus 20 dB. I'm getting 6 because if we just transitioned an octave, we would go down 6 dB. So what's an octave? 8 notes. But in terms of frequency, what's an octave? Do we have some musicians in the house? Any musicians? What's an octave? 8 notes apart, but in terms of frequency. If we now went from A above middle C and then an octave later for A, they would be a factor of 2. So you might be going from 440 to 880 with A. So an octave is a factor of 2. And if we go a factor of 2 over, then we're just changing minus 6 dB. Not that critical, but it allows us to now not have to go all the way over to a decade. We just have to go an octave, a factor of 2 instead of a factor of 10. Yes? So now we'll learn what dB is, but this is now 20 log of the ratio of magnitudes. That's decibels, dB. And you might have heard it when people are talking about sound. But you can also use it for signals. What's the dB change in these signals? And 0 dB is, in absolute sense, a gain of 1. So you take the log of 1. What's the log of 1? 0. You multiply by 20, you still get 0. So 20 log of 1 gives you 0 dB. This now would say, oh, if this is my, let's say, filter, I put in a signal at a frequency of 2 radians per second, I'm going to get out the same amplitude signal out as I put in because the dB is 0 at that frequency. The gain in actual value is 1. It just allows us to add things together when we use a dB. That now takes this magnitude in a logarithmic sense. Just like we've done the frequency, it's now in a logarithmic sense. So looking at it in log or in dB allows us to take the logs of these amplitudes, and that allows us to add them up. A product of A times B, we take the log, it's like the log of A plus the log of B. We get to add things when we take the logs. And I think a few of you are sawing logs. Never mind. No. Another piece of Laplace transforms allows us to play with filters. We did the low-pass filter and filter design. We have a low-pass filter. The lows are being emphasized here versus the higher frequencies. They're rolling off. We're not passing them as easily as the low frequencies. So that's a low pass. We're passing low frequencies more preferentially than other frequencies. Contrast that with high pass. Now we pass the high frequencies more favorably than the low frequencies. And we can come up with different filter types. We can do band pass, where we prefer a certain pass band of frequencies. Maybe we throw away the low, we throw away the high, and now we have the mid-range. That would now be a band pass filter. Or maybe we want to reject a certain set of frequencies. Maybe we want to get rid of the 60 hertz because that's creating a hum in our audio system. So we now put in a band reject filter that's trying to basically reject that 60 hertz waveform. And so this is the rejection band that we are not favoring. We're basically wanting to get rid of it or reject it. And that would be a band reject filter. We'll learn how to design these. Hopefully you appreciate now that this Laplace transform has a lot of useful applications. And we can use it in more domains than just electrical. We will probably emphasize mostly circuits in this class, but we could do mechanical pieces, machines, robots, but robots are a lot of electrical. So if you've wanted to get into robots, it's good that you're in electrical engineering. Just saying. Electromechanical, motors and generators, that's the combination of mechanical and electrical. How do you put in maybe an electrical waveform and get this mechanical shaft to spin That's a motor. That's an electromechanical system, and we can model that with Laplace transforms. Thermal. If you're freezing outside, maybe you go inside and it's now conditioned air. What's the dynamic relationship between that building's contents and what's happening outside? You could model that in Laplace transforms. Or with manufacturing, maybe you have distillation columns, or you're now creating some new chemical, or you have some process. Laplace. Optical, dealing with waves, etc. All of those you can play with using Laplace transforms. Side by side, kitchen and living room again. Time domain, frequency domain. You can draw block diagrams. We'll draw circuits in the time domain and in the frequency domain. We need to get comfortable thinking time domain, frequency domain, and everyone's favorite in the time domain is convolution. Okay, so you've worked with it. You're good friends with this convolution operation. And everybody loves that convolution. You flip and slide. We're actually going to flip and slide waveforms here in this class, and you'll learn to flip and slide waveforms so that we can now do the convolution in the time domain. But if you prefer, you can now multiply these transform expressions and avoid convolution. And you can do the multiplication in the frequency domain. There's the correspondence. Convolution in the time domain can be performed using multiplication in the frequency domain. And that's why we're actually playing a lot in the frequency domain, because we maybe don't want to be doing all of this time domain analysis. So we throw all of our circuit pieces into the frequency domain. We analyze the circuit in the frequency domain. We end up with a voltage. That's maybe what y of s corresponds to. And we want, what is y of t? What's that look like in the time domain? Then we simply do the inverse Laplace and find out what that voltage is in the time domain. All right, wake up. Time for a quiz. We ready? We did so well, I'm going to try not to have blue X's anywhere to confuse everyone. The impulse. In the time domain, that's the impulse. That's what the impulse is, right? It's an infinitely tall, infinitesimally wide waveform, and you excite your system with that impulse. Another way of thinking of that is that impulse initializes your energy storage elements, and then it's gone, and you basically have an initial condition response. And you now know how long it will take for those initial conditions to decay. You'll look at the slowest pole, the pole closest to the imaginary axis, and you'll find its sigma, and you'll say, oh, I need 5 time constants associated with that slowest pole, and that's when all of my transients will have decayed. All right, so what is the Laplace transform of an impulse in the time domain? We've derived this. You don't have to derive this. I'm wondering if you remember what that is. Yes. Was that a question? Slash answer. The question was, is it 1? How many think it's 1? How many are not thinking? At least you're honest. It is 1. Thank you. Shouldn't have been any doubt in your... I believe it's 1, sir. Yes. So it's 1. How about the unit step? What's its Laplace transform? Another answer, or another person answering. What is the Laplace transform of a unit step? Timothy. Is that right? Yeah. Good. Your answer is correct as well. It's 1 over s. Where are the poles in the transform expression for the unit step? How many poles do you have? 1. So it's first order, isn't it? Where is it located? Where is this pole for capital X of s? What determines the pole's location? We evaluate the denominator and we see which values of s cause that denominator to vanish. In this case, you set s, which is the denominator, equal to 0. What s causes that to happen? 0. The pole is at the origin for a unit step. Exponential. What's its Laplace transform? New answerer, a new person answering. And I may come all the way to the back, since that's typically where people sit when they don't want to answer, right? What's the Laplace transform of e to the minus 4t? What does that equal? And I gave it to you actually earlier today in class, did I not? Where this 4 was a sigma, and I said e to the minus sigma t. What was that? Isn't it that? It is. And where's our pole? It's where s plus 4 equals 0, the value of s. It's at s equal to minus 4. See how easy these Laplace transforms are? What's the Laplace transform of the sine of 5t? Now I am going to switch to blue. What is this? What's the Laplace transform of sine of 5t? What's the denominator? Where are the poles? Or, where are they located in the complex S-plane? The poles of a sinusoid. Pardon? Okay, so the response was s over s squared plus 5 squared. Is that correct? So the answer given was s over s squared plus 5 squared. How many are in agreement on that? What? You disagree? Why do you disagree? So this is the Laplace transform of what? That's the cosine. It is a sinusoid at 5 radians per second, but it's a cosine. So the cosine and sine have slightly different Laplace transforms. In this case, for the sine, instead of s, we don't have a finite 0, and it's not at the origin. Omega goes here, so we have 5 over s squared plus omega squared, and omega is 5. This is now the Laplace transform of this waveform, and I could have written it as sine 5t u of t. I've used the unit step as the switch. The only time this sine of 5t will be active is when this u of t is 1, and that occurs only when t, the argument of that unit step, is non-negative, when t is greater than or equal to 0. What if I changed this and I said, well, what if we had 7 times sine of 5t? What would its Laplace transform look like? The Laplace transform's a linear operation, isn't it? So we would just scale that transform by 7, and we could say, oh, it's 7 times or it's 35 over s squared plus 5 squared. We didn't change the denominator because we didn't change the frequency of that sinusoid. What about cosine of 5t? Pardon?
I agree with his answer.
Oh, now the earlier answer is correct, is what you're saying? Everybody okay with that? What if I did the following? What if I said there's a 6? Now we just scale that by 6. Don't need to change anything else. The s over s squared plus 5 squared is still okay. Now you guys should be feeling all warm and fuzzy, right, after that quiz. What about these waveforms? Exam number 2, we're getting ready. Well, you have all spring break to chill about exam number 2, right? So this is what you might see on exam 2. The first one, what's going on with the first one? I've tried to draw an illustration of what's happening. It switches on at time t equal to 1.5. When the argument of this is 0, and then for all t after that, the argument of u of t minus 1.5 will be non-negative. I've turned a cosine on after 1.5 seconds, and it just keeps going and going. And that's what x sub 1 of t is. But if you didn't want to just drop back and punt or throw in a blank piece of paper on the exam, what would be a good partial credit answer without doing too much work for x sub 1 of t, for the Laplace transform of that? You might just say, well, I'm sorry, I don't know what that one is, but I can give you cosine of 4t, can't you? You'd say, oh, let me show you what the cosine of 4t, at least I studied a little, right? And then you would give me that. And then you would say, okay, it's probably going to be some modified form of the Laplace transform of cosine of 4t. Here, what do we call this waveform for x sub 2? What did we call that earlier today? A damped sinusoid, right? An exponentially damped sinusoid, and in particular, it's a cosine. And we have a cosine of 5t. We just found out what that looked like. We now need to do an exponential decay on that, and we'll learn what that looks like once we talk about operational transforms, which are covered in table 12.2. But before we get there, before we talk about operational transforms, let's look at the Laplace transform of this. What does the Laplace transform of a pulse look like? Have we computed the Laplace transform of a pulse yet? And if we have not, is there a way that we can rewrite this or write this as a combination of waveforms that we have already Laplace transformed? Here's the question that I'm now asking. I'm asking, can we rewrite z of t in terms of what I will call standard waveforms? And I saw some heads bobbing up and down saying, yes, we can do that. What does this z of t look like in terms of common waveforms that we've already studied or standard waveforms that we've already examined? Okay, it's really just a linear combination of shifted unit steps and scaled if the amplitude is A. Or we're really looking at z of t is now z1 of t minus z sub 2 of t, where z sub 1 of t is that unit step, and z sub 2 of t is right there. And we know how to find the Laplace transform of z1. We know how to find the Laplace transform of z2. And the Laplace transform is a linear operation. And so we can combine those results. Or we can now say that the Laplace transform of this pulse, which we called z of t, is now the Laplace transform of z sub 1 of t minus the Laplace transform of z sub 2 of t. And what's the Laplace transform of z sub 1? What's the Laplace transform of a unit step? That was one of the first, that was the second row in our quiz, wasn't it? 1 over s. Now we scale it by a, it's a over s, but now we've delayed it by t1. Do you remember what happened when we delayed Laplace transforms? They were scaled by an exponential, consistent with the amount of delay. Or the Laplace transform now of z sub 1 is a over s. That's a scaled unit step. But now when we delayed it, we had to weight it by e to the minus s, the amount of delay, t sub 1. If that's the Laplace transform of z sub 1, what's the Laplace transform of z sub 2? I'll do the hard part. A over s. But the other part's not much more difficult because it is exactly the same as what we did with z1. It's just we have a longer delay. And that longer delay is of a value t sub 2. And we could now rewrite this and we could say, oh, that's a times basically the Laplace transform of a unit step that's just now been delayed in two different ways. We have e to the minus s t1 minus e to the minus s t sub 2, and that's now the Laplace transform of a pulse. Somebody was trying to get home so they could rederive this. A pulse of amplitude A, and it has a width of t sub 2 minus t sub 1. Let's now look at some operational transforms. Because what we're wanting to do is be able to figure out how do we use not only the tables, but also operations to allow us to come up with Laplace transforms for these uglier looking waveforms. or more challenging waveforms. The first one deals with translation in time. When we typically translate in time, it's usually a delay. And if our waveform is delayed by an amount t sub 0 and we turn it on at that exact same location that it's delayed for, then if we knew the original f of t's Laplace transform, which was, let's say, capital F of s, we simply scale that by e to the minus s, the amount of the delay. And that's what we used actually in that pulse Laplace transform. We used this operational transform to find that. Another operational transform, instead of translating in time, let's translate in frequency. And it's going to look similar to what we just have in row 1, except we're going to be doing the exponential in the time domain. So that now we have e to the minus at scaling f of t. And we've seen this. We did an exponentially damped cosine. So if we knew the Laplace transform of the cosine, which is f of t, then we can figure out how to find its Laplace transform if we know how much exponential decay is used to scale that cosine. Or now, if we knew that little f of t had a transform capital F of s, everywhere we have the s, we replace it with a translated frequency, with the translation in the frequency being a value a. And that's what we saw when we had this e to the minus sigma t cosine omega t. We replaced s with s plus sigma everywhere. One more transform operation, scaling. Suppose that we now have scaled the time variable in our time domain waveform by a, where a is, let's say, a positive scaling factor. Then we would simply, everywhere we had an f of s, we would scale the frequency by dividing by a and scale the whole transform expression by 1 over a. And you can see that time and frequency are reciprocally related, correct? And that's what a is doing. It's sort of coming in the reciprocal location in the time domain versus the frequency domain in our scaling of the frequency axis. Let's now look at some examples of applying that. Suppose we are given x sub a of t to equal cosine of 4t u of t. Or another way of thinking of that is that's now cosine of 4t for t greater than or equal to 0, and it's 0 for all time less than 0. That's the way that we're using this multiplication by the switch, or the multiplication by the unit step. This one we should be able to do, right? It really hasn't translated anything in time. What is capital X sub a of s? And now this is consistent with some earlier answers. This is the cosine. The key piece of this is what? Finding its frequency, finding its omega, and its omega is 4. And that 4 gets squared downstairs. It's now that's the denominator, and the cosine has a finite 0. The sine has the frequency upstairs. If that's now x sub a, let's look at a translated version of that. Suppose now we say x sub b of t is now going to be cosine of 4t minus 6 for t greater than or equal to 1.5 and 0 for t less than 1.5. Or this is the same as saying cosine of 4t minus 6 u of t minus 1.5. And I've actually set this up to be a convenient argument in the cosine. Let's look at the cosine argument to try to understand what I'm meaning by that. The argument of that cosine waveform is simply 4t minus 6. But if we factor out the frequency omega from both terms in that combination of terms, how many times does 4 go into 6? 1.5. So this is now that 4t minus 6 is in fact 4 times the quantity t minus 1.5. Or maybe I should do it in a couple of steps. This is now 6 over 4, so that it's clear what I've done. Or we can now rewrite x sub b of t as cosine 4 t minus 1.5 times u of t minus 1.5. And the key observation is to realize that the delay and when we turn this cosine on is consistent with where this cosine is actually starting its maximum value. So these arguments are consistent. And this 1.5 is in fact the amount of the delay. Now we can use that first operational transform to produce capital X sub b of s. And if you were looking for partial credit, what would you do? You would just say s over s squared plus 4 squared, and you would say, oh, I forgot how to translate for the delay. But if you remember, then you can simply say, oh, it's e to the minus s times 1.5, or e to the minus 1.5s. What if we did the following? What if I now gave you x sub c of t, which is now cosine of 3t minus 5 u of t minus 1.5. And what have I done here? I've actually thrown you a little bit of a curve, have I not? Because if I factor 3 out of 5, is 3 times 1.5 5? No. 3 times, if you have 15 cents and you get 3 of those, it's 45 cents, right? So it's now 3 times 1.5 gives you 4.5, and that's not 5. So I've messed things up here. If we looked at the cosine argument, we can now say, oh, we have 3t minus 5. And what I'm wanting that to look like is that. Because then I can equally or easily factor out the 3. But I don't have 3t minus 4.5. I actually have 3t minus 5, so I have to take another half off. But this is now 3 times t minus 1.5 minus 0.5. And in my cosine expression, I now have a plus b. And I can use some trig, cosine of a plus b, to account for this a little additional piece that now is in my argument of the cosine waveform. We're out of time. I appreciate your patience. We'll try to, I don't know, maybe I'll fill in some more of these after class. I'll decide what I do. Maybe you might look for notes after class, but hopefully you're getting the hang of this.